Thanks. I'll begin with a word of prayer. Heavenly Father, we thank you for this day. I thank you for the students. Just ask you to bless this class, Lord. In your name I pray. Amen. All right, so we were nearing the end of my discussion of series because I don't spend a lot of time on series this semester. So there's in a typical semester in here, I often cover something called the Frobenius method, which shows you how to solve series, solve problems that are related to the ones we're doing, but at what's called a regular singular point. The Cauchy-Euler problem is the sort of most basic example of a Frobenius problem, but there's a whole world of these Frobenius solutions that we don't get into in here. But if you understand the series method I'm showing you right now, it's a relatively straightforward thing to extend to the Frobenius. It's just the calculations for the Frobenius method are, I don't know, 2-3 times harder than what we're doing. So it's well enough. I'll leave it for your future study. So let's look at an example. Again, I don't cover the Frobenius method this semester, but let me show you an example here. So let's try to solve, let's say, y prime prime plus 3, let's say x squared y equals to 0. So, and we're going to try to find the solution centered about 0. Now, first of all, that's going to be possible because the coefficients of this differential equation are what? 1 and 3x squared. Where's 3x squared have a divergence? Where's there a singularity in the 3x squared function? The answer is nowhere. All right, so hooray. This is an ordinary differential equation. I mean, like any point is ordinary. You could find a solution expanded around any point. You could do it. Unlike the example I did at the very tail end of the last class we had before the class participation. So let's see here. So the game plan is to write y equals to the sum, and I'll use n because my n's are easy to read. N equals 0 to infinity of, let's say, a sub n, x to the n. And with that in mind, we get y prime is the sum. N equals 0, well, we could write 0 to infinity, but I'm going to write 1 to infinity because, you know, what's the derivative of x to the n? It's n, right, times x to the n minus 1. So this is term-by-term calculus. Now, I could write out the first few terms in both of these just so you have a little bit better sense of what we're doing. This is a0 plus a1x plus a2x squared plus da-da-da, right? This is just a1 plus 2a2 plus 3a3 x, well, there's an x here, right? 3a3x squared plus da-da-da. What I wrote off to the right here, we don't really even need to write. I'm just writing it there for pedagogical reasons at the moment. And then take a second derivative, y prime prime. Well, that's going to be the sum, n equals 2 to infinity, of a sub n times n minus 1, x to the n minus 2. All right? Which, of course, if you're keeping track, would be 2a2 plus 6a3x and so forth. All right. Now, our goal is to pin down these coefficients, a0, a1, so forth and so on, and try to relate them. We know that this can be done because we have a fundamental theorem which says that, hey, this is a linear second-order differential equation. We know that the general solution should be able to be written in terms of two linearly independent fundamental solutions with two constants, like a C1. So the solution should end up being like C1y1 plus C2y2, right? That's what we're looking for. And we have an embarrassment of riches at the moment. We have infinitely many constants. It's too many. We need to pin them down. So what we're going to do is we're going to substitute these up into there and see what happens. All right? So substituting into the differential equation, what do we got? we have y prime prime, which remember was the sum, n equals 2 to infinity, of a sub n times n minus 1 times x to the n minus 2. That's my y prime prime term. And then plus 3x squared sum n equals 0 to infinity of a sub n x to the n. Now that's all equal to 0. So let's clean this up just a little bit. So what we really have is the sum, fine, I'll just write it again, n equals 2 to infinity, a sub n minus 1, x to the n minus 2. I'm just copying. And then over here, we're going to have plus what? Plus the sum n equals 0 to infinity of 3 a sub n times x to the what? X to the n plus 2. So in order to add series, right, you have to have them have matching indices. Like the powers structure has to match up. And we don't have that right now. We've got an n minus 2 index here, right, like an n minus 2 format, x to the n minus 2. Over here we have the format x to the n plus 2. We want to make them look the same, right? So my suggestion would be, let's think about it. You know what? I'm going to change both just to get you more experience in the changing. Let's change both of them to just to the power j. All right. So here we'll let this in this side we're going to make a substitution j equals n minus 2. Over here I'm going to make a substitution j equals to n plus 2. These are separate substitutions, obviously, right? Can't have both of those at the same time. And if I put j equals to n minus 2, what's that say? N times n minus 1 is actually equal to what? Well, before I get to that, what's n equal to? Yeah, n equals j plus 2, right? So a sub n is a sub j plus 2, right? And what's n times n minus 1 in this side? N times n minus 1 equals to j plus 2 times j plus 1. All right. So that's going to allow me to make the substitution to j on the left term. On the right term, we've got n equals to what? J minus 2, right? And so a sub n there is a sub j minus 2. All right. So with those substitutions in mind, that gets us to the following. We get the sum. Oh, I forgot the most important part. Now n equals 2. What does that say? J equals to what? Zero. Very good. Yep. So this one starts from 0. How about the other one? Let me finish writing this one, though. That's a sub j plus 2 times j plus 2 times j plus 1, x to the power j, and then plus the sum, j equals to something. And then we've got 3, a sub j minus 2, x to the power j. Where's j start over here? J, n equals 0 says what about j? Yeah, j equals 2. So the other sum starts at 2. So we can add these sums because now we have reformatted both so that they match up, right? Now we can add them. We can combine the series. However, be careful. The first one has a couple of exceptional cases, right, which we should write on their lonesome. Like j equals 0 gives me what? I get an a sub 2 times 2 times 1, right? X to the power 0. And then I get plus what? Plus a sub 3. So this is, I'll tell you, this is the j equals 0 term. Here's the j equals 1 term, which would be a sub 3 times 3 times 2, x to the 1. And then we're to 2, so we'll throw 2 and beyond together into one big old series over here. Sum j equals 2 to infinity. And so we've got, I'm going to write the j's first, j plus 2 times j plus 1, a sub j plus 2, plus 3 times a sub j minus 2, all times x to the power j. And this is equal to what? Yeah, 0 equals to all this. Now, how can we have a series be 0 for all x, right? What has to be the case? We must have that every coefficient of the series is 0. So on the test you guys just took, you did equating coefficients for like how many things? 2, 3, 4, maybe, right? Now we're going to equate coefficients infinitely many times. 1 for each power of x. So let's do it. How about the 0th power? What do we get from that? What are the 0th power terms here? We just get 2a2, right? Equal to 0, which tells us what? a2 is equal to 0. Hey, 1 down, infinitely more to go. How about j equals to 1? Sorry, I'm an idiot. J equals 1, I've got 6a3, again, equal to 0. What does that tell us? It tells us a3 is equal to 0. What's suspiciously absent from this story? How about a sub 0 and a sub 1? Nothing to say there, right? Not yet, anyway. Now, what's next? And then, for j greater than or equal to 2, we have the following relation. We have that j plus 2 times j plus 1 times a sub j plus 2 plus 3 times a sub j minus 2 is equal to 0. And so let me repackage that ever so slightly. Let's say that what that's saying is that a sub j plus 2 is equal to minus 3 a sub j minus 2 over j plus 2 times j plus 1 for j greater than or equal to 2 again, right? Now, writing things in terms of j has served us well, but I think it's time to give up on j. All right, I think we should divorce ourselves from j and go back to n at this point. So let me say that we could let n equal to j plus 2, right? Let n equal to j plus 2, and that's going to be more fun. If n is, let n be, rather j minus 2, I should say. I don't know, you can go either way. What do you guys want? I said j plus 2. N equals j plus 2. What's that say about j minus 2? N minus 4, right? J minus 2 would be n minus 4. Yes, sir?
So it doesn't, because we have two different definitions for n.
Yes, we are changing the meaning as we go.
Oh, okay.
You could put m there if it's bothersome. You know, that'd be fine.
So this n is not the same as the original?
No, the original n is, I mean, these are dummy variables of summation, right? So if you wanted me to be really fussy, we probably shouldn't even use the same n here and here because they're different n, really. Right? That's the first summation, that's the second summation. If you're writing computer code, you wouldn't want to use the same variable for both because they're logically separate sums. Okay, so operator overloading. A sub, what we got here? A sub n plus a sub n is equal to minus 3 a sub n minus 4 divided by what? Divided by n times n minus 1. See, this is going to be for n what? N greater than or equal to 4, right? And my point is, what I'm about to circle here is not the answer, but it's awful close to it. I mean, this is a nice, clean, crisp, clean-cut version of the recurrence relation, which essentially will define the solution for us. Any problem of this form works out like this, essentially. You plug in the series to the differential equation, work it out carefully, and after things filter through, you should be able to derive one or two recurrence relations, which fix future coefficients in terms of past coefficients. If we think about, the past being the earlier ones and the future going to infinity, think of coefficients in some sort of temporal order. Sorry, I've been watching too much Star Trek. It's like a channel that's playing 5 hours of Star Trek. They start out with like the old cowboys and like the cowboy one with what's his name there, the guy who talks funny, or he has a particular way of talking. No, not the Spock. Well, Spock was his contemporary. Rest in peace. He's like 85 now. This guy's still alive. One of the more iconic actors of our time. What's his name? Oh, good grief. Shatner. So there's that one, the original Star Trek, and then they've got Star Trek The Next Generation. And then after that, they play Star Trek Deep Space Nine. I'm like, whatever. And then after that, they play the other one. What's that one? What's the after Deep Space Nine?
The one with the woman captain?
Oh, right, the one that teaches us that woman captain makes mistakes, right? That one?
Yeah, that's the one.
It's not a very good feminist vehicle, really. Every mistake she makes has to be fixed by that man on the show. Think about it. It's not good. This is not my observation. It was a friend of mine. I'm just repeating what I was told, just in case, And then there's one after that. I don't know if they have the more recent one. I don't know. I lose track of my Star Trek. Oh, yes. Okay, so let's go on. What does it say? This circled equation says that there's this linking there's like this fourplicity to the answer, right? What does this say? So to understand this, I usually start writing some things down. Like, what's a sub 4? It's minus 3 a sub 0 divided by what? 4 times 3, right? And what's a sub 8? It's minus 3a sub 4 divided by 8 times 7, yeah? Which is what? Which is really, minus 3 over 8 times 7 times minus 3a sub 0. You're like, you could cancel the 3's. Yes, I could, I know. I didn't, sorry. And what happens with a sub 12? Right? Maybe you start to see a pattern here, right? Maybe we can see a pattern. What is a sub 4k equal to? So this was 3k, right? This was, this was k equal to 3. This was 4 times 3, right? This was 4 times 2. This was 4 times 1. So in other words, this is my k equals 1. This is my k equals 2. This is my k equals 3. Can you see the pattern? Minus 1 to the what? I think we've got a minus 1 to the k, right? And how many copies of 3 do we have upstairs? Yeah, we've got k copies of it. So we could simplify, right? We could say 3 to the k minus 1. Just go ahead and cancel those 3's like I could have been doing from the start, right? Cancel the 3. And then what's left? Divided by what? Well, I've got 4k, right? Times 4k minus 1, right? Dot times what? Times 12 times 11 times 8 times 7 times 4, because I canceled the 3 out. And all of that times a sub 0. And that's about the best answer I can give you for these coefficients. This is not the answer yet, but that's about as clean as I can make it, all right? So if you can do this for 4, I mean, if you think about the natural numbers with 0, what do you got? If you think about the natural numbers and throw in 0, you can divide them up like this. You've got 0 unioned with like 4n, and then you've got that with like 4n plus 1. You've got the things that have the, let me just say, let me call this thing n sub 0, n sub 0, just to throw in 0 because I'm getting tired of this. 4n sub 0, 4n sub 0 plus 1, 4n sub 0 plus 2, 4n sub 0 plus 3. If you think about numbers, counting numbers, you can partition them. Multiples of 4, multiples of 4 plus 1, multiples of 4 plus 2, multiples of 4 plus 3. This gets every single possible number, right? So all of our coefficients fit into one of these 4 classes. We figured out what happens for 1/4 of the universe of coefficients at this point. Let me do the easy ones next. What's the easy ones? Okay, fine, I'll do the not so easy ones. What's the other not so easy case? A sub 5 is what? Minus 3 a sub 1 over what? 5 times 4, right? And what's a sub 9? Minus 3 a sub 5 over 9 times 8, which is minus 3 over 9 times 8 times minus 3 a sub 1 over 5 times 4. And then what's a sub 13? It's minus 3 a sub 9 divided by 13 times 12, which when we plug in the previous one, we've got minus 3 over 13 times 12 times minus 3 over 9 times 8 minus 3a1 over 5 times 4. Maybe you can see the pattern again. What's the pattern? A sub 4k plus 1 equals apparently minus 1 to the k, 3 to the k this time because the 3 didn't cancel. And downstairs we've got 4k plus 1 times 4k times 13 times 12 times 9 times 8 times 5 times 4. And all of that times a sub 1. So 4k plus 1 coefficients work out like that. Yes, Ian?
Is there a reason on that first one why you're writing the numerator as negative 1 to the k times 3 to the k minus 1 instead of just negative 2 to the k? Am I missing something really obvious?
I could do this.
Oh, I see. Okay.
Yeah, there you go. But then you would have asked me why I didn't cancel out the 3. So anyway, I lose. I know. You got me. There's no chance for me to survive. Okay, so how about, on the other hand, you got your a sub 4k plus 2, which is what? This is equal to 0. And why is a sub 4k plus 3 equals to 0? Why are these all 0? Why is this the case? Can you see why that is? Because we have, for example, a sub 6 equals to what? A sub 6 is equal to minus 3 a sub 2 over 6 times 5, right? Which is minus 3 over 30 times 0. Because we know that a sub 2 is 0 from our earlier equating coefficients, right? So the fact that the second coefficient is 0, and the fact that the fourth, when you add 4 to the index, it's directly related to the 1, 4 before it. If one of them's 0, then they become 0 all the way on out. So like the fact that a sub 2 is 0 forces a sub 6 to be 0, forces a sub 10 to be 0, a sub 14, 18, 22, we get the idea. And likewise, a sub 4k plus 3 is going to be 0 because we already proved that a sub 3 is 0. And so like a sub 7 would be related to minus 3a sub 3 over 7 times 6, which again would be 0. So the answer, right, I'll write over here, yields y equals to the sum, and I'll use k because it's convenient, k equals 1 to infinity of, what was it, a sub, well, I'm going to pull that constant out front if you don't mind. Let's see, the first one, a sub 0, pull that out front here, and then I got myself minus 1 to the k, 3 to the k, over, what was it, 4k times 4k minus 1, times 8 times 7 times 4 times 3. I mean, I had a better pattern over there, fine. And that's all to the x to the what power? In our solution, a sub n is paired with x to the n, right? This is a sub 4k, so it's paired with x to the 4k, right? And then plus a sub 1 sum k equals 1 to infinity of minus 1 to the k, 3 to the power k, over 4k minus 1, or was it plus 1? I can't remember. Yeah, 4k minus 1 times 4k, times 9 times 8 times 5 times 4. Where's that? What, plus what? What?
Yeah.
Did I do it wrong? Oh, 4k plus 1. Oh, yes, thank you. 4k plus 1, yes. Thank you. 4k plus 1, And all of that times x to the what? X to the 4k plus 1, right? Now, what I'm about to put in some red parentheses this is y1, this is your y2. y1 and y2 form the fundamental solution set here. Now, I don't have y1 and y2 in terms of like things that are pretty, like sines and cosines and exponentials and polynomials, but hey, there are series formulas for y1 and y2, which is as good as we can do here. Unless you want to give a name to these things. Like we could call this the Drake function, and this would be what? Kanye's hat function. I don't know. What do you want? No? Is it too soon? I used to have a make math great again sticker I had on my computer. But I had to take it off at some point because I had to go talk at a conference somewhere, and I don't know.
What happened?
Trump's kind of a sore. Oh, math always needs to be made great again. It's just the ongoing story of our time. I mean, it's not always appreciated, but it's true. Ahem. So there you go. Now, if you remember your calculus 2, there's all kinds of interesting questions you can answer immediately from this. Like, if you look at the solution, what's the derivative of the, I don't know, Let me think about something. What's the 22nd derivative of this evaluated at 0 equal to? What's that? Death, pain, and torture. Well, fortunately, those things are 0 here. Because I don't think 22 fits into either of these classes, right? Like this one, it's 20 when k equals 5, then it jumps to 24, right? If 22 is equal to what? 4k plus what? 2, right? Where k equals 5. So we know Taylor's theorem says that if we take the solution and we calculate the k derivative of it, we evaluate it at 0, we divide by k factorial. Maybe I should use something other than k. Let's use m. Yeah, I know. Operator overloading. This will be equal to, well, a sub m. So if I give you an m which has a coefficient of 0, like 22, there's no 20. The coefficient of x to the 22nd power is 0. I can tell you immediately that the derivative at 0 of the solution, 22nd derivative of the solution at 0 is 0. You may or may not recall this kind of question from calculus 2. Seems like many of you have forgotten. I'll put it on the next quiz. Okay, so. This is a muted groan. Let's see here. Maybe not so muted. All right, so anyway, that's how you do these problems. Now, there's another way we can ask these kind of questions, which is just find the first few terms. This is the complete power series solution, right? Let's look at a problem where I'm just going to find the first, let's say, well, let's find the solution to quadratic order. Let's do that. Let's find the solution to quadratic order for one of these problems. Let's see here. Oftentimes, this is all you need for an application because the first few terms may suffice to approximate the model you're interested in. So let's see here. Suppose we were solving y prime prime plus, oh, I don't know, 3 plus x squared y equal to 0. And we wish to find solution to order 2, centered at 0. So this one here, if you have a problem like this, the summation notation is not what you want to go with. You want to use the plus dot dot notation. That's like way more efficient for this sort of problem. But the general technique is still the same. We just start with saying, okay, well, I'm going to let y equals to a sub 0 plus a sub 1x plus a sub 2x squared plus dot dot dot. All right? And that may be enough. Sometimes you have to take higher order. What happens when we differentiate 2 times? We get what? 2a2 plus higher order things like what's next? 6a3x, right? Yeah, I still have it over here, right? Okay, well, that's what my second derivative of my template solution looks like. Now plug it in. And that gives us 2a2 plus 6a3x plus, man, I want to keep the next term if you guys don't mind. What's past 6a3? Is it 12? 12a4x squared? Think about this. This is a 3x cubed plus a 4x to the 4th. If I twice differentiate that, do I get this? 4, 3. Yeah, okay. I'm just going to throw it in there just for good measure. We probably don't even need it. I may actually find a little bit more than I asked. I'm not being as lazy as I maybe should be here, okay? And then plus 3 plus x squared, right, times y. What was y? A0 plus a1x plus a2x squared, like that. Now all of that's equal to 0. And then what we do is we just, I mean, you could multiply this out. I would discourage you from doing that. I think at this point, the wise thing to do is just start thinking term by term, trying to find equations for the constant, for the linear term, for the quadratic term, and so forth. We can equate coefficients, right? Because for this to be a solution, we must have 0 term by term by term. And so let's get started here. How about the constants? What do we got? I got a 2a2 it's sitting there. Nothing, nothing. Over here, 3 times a naught, right? Anything else? No, I mean, 3 times any of this has got an x. X squared times anything's got an x. So that's it. These are the constant terms. That's all there is. And that has to be equal to 0. So therefore, we have that a2 is minus 3 halves a naught. Yay. All right. How about x? What do we got for x? We've got 6a3. All right. Well, that's it for that. Over here, I've got 3 times a1, and that's it from the 3. Is x squared times anything going to give me an x? No. So that does not contribute. So we have 3a3 plus 3a1 equal to 0. Therefore, a3 is apparently minus 1/2 a1. We're always looking to relate the higher coefficients to a couple of the lower coefficients. That's the typical pattern. All right. Next up, x squared. What do we got for x squared? We got a 12a4 plus what? Oh, equal, plus, okay, x squared. So I've got 3a2. And finally, Mr. X squared is contributing something. What's he contribute? A sub 0, right? So plus a sub 0 here. Are there any other quadratic terms? Nah, that's it. That's it. So therefore, let's see here. A4 is equal to minus 3a2 minus a sub 0 over 12. Can we simplify that? Yes, we can, right? Because this a2 is that a2. So that's really what? Looks like it's 9 halves a sub 0. What's 9 halves minus 1? So, yeah, 7 halves. So 7/24, I think. A sub 0 there. Because I get the 7 halves divided by 12, which is 7/24. I do make arithmetic mistakes. If I've made one, let me know. I'm going to stop there. So actually, I've done more than I asked us to in the start. I have now derived enough to write the solution to fourth order. Right? I can write the solution to quartic order. Here's the solution. Y equals to a sub 0 plus a sub 1x plus a sub 2x squared plus a sub 3x cubed plus a sub 4x to the fourth plus dot 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 dot, which is equal to actually what? It's equal to a sub 0 times what? Well, you got a 1. How about a sub 2? Minus 3 halves x squared. And, well, we figured out a fourth was plus 7/24 x to the fourth plus dot 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 dot, right? And then plus a1 times what? Well, x. Of course, the x is there. And what was a3? Oh, minus 1/2 x cubed, and then I don't have past that. That's it. That's all I got. So this is actually the solution to fourth order. All right. So if I was asking you to calculate the solution to fifth order, and you gave me this, I'd be like, 1, 2, 3, 4, 5/6 partial credit, right? Well, maybe more. I don't know. But does that make sense? So there's really no need for the sigma notation in this kind of problem. If you're just looking for the first few terms in the solution, this does nicely. Should we look at another one? Let's look at another one. This will be our final example. I can do these for 2 weeks, but until you sit down and try to do one for yourself, it won't really mean much to you. It's much better for me to go slow, like I did for the first example, as opposed to cover 3 fast or something. All right, so next example. So suppose we have e to the x, y prime prime, plus sine of x, y prime, plus 1 over 1 minus x squared, y equals to 0. I want to find the solution, let's say to fourth order. Centered at 0 again. So this kind of problem, for power series calculation to work, what you have to do is it's pretty simple, really. You just have to convert everything in sight to power series. If you convert half of the things in sight to power series, but leave e to the x, it's not going to work. If you leave 1 over 1 minus x squared not in series form, it's not going to work. Everything on the board must be converted to series form, from the template solution to the given coefficients. By the way, all of those coefficients are non-singular at 0. So 0 is a regular point, an ordinary point. Now we know power series for e to the x, right? E to the x is what? It's 1 plus x plus 1/2 x squared plus dot 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 dot, right? That's my e to the x. And then, what's my sine of x? Well, sine of x has the power series x minus 1/6 x cubed plus dot 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 dot. That's probably going to be enough for us there. And my 1 over 1 minus x squared, well, that's a geometric series. That's 1 plus x squared plus x to the 4th. Although I don't even need the x to the 4th, so I'm not even going to write it. 1 plus x squared plus dot 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 dot. Why? Oh, maybe I will, actually. I'm sorry. I'll get with the program here eventually. X to the 4th plus dot dot dot. Why? So I need to convert the coefficients to their series representations, Maclaurin series representations, since we're centering at 0. And then, okay, well, and then we just do what we did before. What was y prime prime? It was 2a2 plus 6a3x plus 12a4x squared. And then I've got x minus 1/6 x cubed. What's y prime? It's a1 plus 2a2x plus 3a3x squared plus 4a4 x cubed. I probably don't need all this, but 4a4x cubed. That might be enough for me. I'm going to stop there. You know, you can always add more terms in later if you find out you need them. 1 plus x squared plus x to the 4th. And then my y, a0 plus a1x plus a2x squared. Should have got a bigger board. a3x cubed plus a4x to the fourth. All of this is equal to 0. All right. This seems like a little bit more fun. All right, so the constant coefficients here, what are they? Well, I've got a 2a2 from the first product, right? And that's it. How about this one? Ooh, x's. Nothing here. And over here, I've got 1 times a0. So I get 2a2 plus a0 equals to 0. So a2 is minus 1/2 a sub 0 again. What'd I do? Yes, but x. It's not a constant term. That'll appear in the next chapter in our story. Looking for coefficients of x, we've got 1 times 6a3. We've got 6a3, but we also have a 2a2, right? Just from the first term. Now here's your x plus a1. And that's it. Anything else has higher x's. Over here, we have a1 again from 1 times a1. But what else do we have? Well, that's it, because next thing is x squared, and I can't take x squared times something and get back an x. Those are my 4 x terms. Therefore, a3 is equal to what? Minus 2a1 minus 2a2 divided by 6. Let's clean that up, because we know that a2 can be rewritten in terms of a sub naught, and you always want to clear out higher coefficients in terms in favor of lower coefficients whenever you can. And this is such a case, because that a2, we already have that up there. So we clean that out. That gives us what? What's that? Plus a sub 0, right? So I get minus a1 over 3, I think, plus a sub 0 over 6. At this point, I've already got the solution to third order, because I know what a sub 3 is. I think this is the funny thing, right? We only looked at the x coefficient, but it got us the third order solution. That's kind of neat, isn't it? X squared. What's the deal with x squared? So you got your 12a4. We've got plus 6a3. And then plus 1/2 times 2, which gives me plus a2. Right? Let me draw what I just did. To get these 3 terms, I did this times this, I did this times that, and I looked at that times that. That was all to get these 3. How can we isolate x squared over... Is there any x squared in here? Yeah, there is. X times 2a2, so I get a plus 2a2 there. Anything more? Is there any other way to get x squared from multiplying these? Oh, x cubed always creates something third order or higher. That's no help to us. So it's just that one. Great. Now over here, we've got the 1 times a2, so I got plus a2. And we've got x squared times a sub naught, so I got plus a naught, right? Anything else? I think that's it. So that's equal to 0. Of course, what we're after here is a sub 4. So we've got a sub 4 is equal to, what we got? Minus 6a3. How many a2s do we got? 1, 3, 4. Minus 4 a2s. Minus an a sub 0 all divided by 12. Now we should simplify that, right? You need to simplify it as much as you can. The proper answer here. So we already know what a sub, we can put this a sub 3, right? We've got this nice relation up here. So we got to put that in there. So we've got minus 1/2 of a sub 3, but a sub 3 is minus a sub 1 over 3 plus a sub naught over 6 from the green. And then what's 4/12? It's minus 1/3, right? And what's my a sub 2? It's minus 1/2 a sub naught. And then, of course, then I've got minus 1/12 a sub naught. So let's clean that up. How many a sub naughts do we got? Got minus a 12th plus a 6th minus another 12th. Hey, how many is that? What's minus 1/12 plus minus 1/12 plus 1/6? It is 0. Yes, there's the a sub naught terms cancel out. Cool. And what are we left with? Looks like plus 1/6 a sub 1. Right? All right, so let's put it all together. What do we got? Y equals to a sub 0 plus a sub 1x plus a sub 2x squared plus a sub 3x cubed plus a sub 4x to the 4th, which is equal to what? We got a sub 0. What was my a1? It's just, well, a1x, right? What's my a2? Minus 1/2 a naught x squared, yeah. And then what's my a4 is interesting, right? Oh, what's a3? A3 is the interesting one, actually. A3 is minus a1 over 3 plus a naught over 6 x cubed, and then finally plus 1/6 a1 x to the 4th. Now we can clean that up. What's our we have a sub 0 times what function? 1 minus 1/2 x squared, right? Where else is a sub naught appearing? Oh, over here, plus 1/6 x cubed. And I think that's it for now, plus dot dot dot. And then a sub 1, what? You got your x. Any other a sub 1s here? Nope, no. Oh, minus 1/3 x cubed plus 1/6 x to the 4th plus dot dot dot. There you go. That's the solution to 4th order. So I hope I've shown you enough that you see that the method is actually very straightforward. Perhaps tedious, right? But straightforward. I don't know if you, I hope you realize this in Calculus 2 as well. This is a method of integration, right? You can pretty much integrate anything if you're willing to look for a series solution to it, right? If you just take the function you're integrating, find its power series, you can integrate term by term, and in so doing, find a power series solution to the problem, right? In some sense, when I found that in Calc 2, I was like, oh, why did I spend all that time on like integration by parts and partial fractions and all that other stuff? I could always just do the series thing, you know? It actually finds an explicit answer, and it also gives me a method for approximating the function to arbitrary order. Yeah? It's kind of nice. But we like our elementary functions, so there you go. All right. So our next topic, which we shall begin now, is what? What's next? Why solve one differential equation when you can solve many, right? So now we are going to study systems of differential equations. So that's the next topic, systems of differential equations. And to be more truthful, systems of linear ordinary differential equations. So my first order of business is to convince you that if we're studying a system of differential equations, linear differential equations, it in fact is sufficient to just study first order differential equations. Let me show you why. So here's an example. If we had y prime prime plus 3y prime plus 2y equals to 0, and we had x prime prime plus y prime prime plus x equals to 0, like this. This is two differential equations, a system of two differential equations. Now, to make this more interesting, I'm going to change this first y to an x. And the reason I'm going to do that is otherwise we could actually solve it. Because you could just solve the first one and then plug the solution of the first one into the second one, and you could go down on that. In other words, you could just you could find a brute force solution to this with what we already know. I wanted to make it a little bit more complicated than that. I'm not actually going to solve this. But what I'm going to do is I'm going to show you that there is an equivalent system of first order differential equations which we could trade for this one instead. And here's how you do that. So this is called reduction of order. So it's very simple. We let x1 equal to, pick a variable, let's say y, and then x2 will be y prime. All right, that'll be enough for y. And then we're going to let x3 equal to x, and we're going to let x4 be equal to x prime. So my claim is that we can recast these two second-order differential equations as a corresponding system of four first-order differential equations. So first of all, let's just look at my definition. What's this tell us right here? This one translates to what? What's x2 prime? Y prime prime, right? And this one, what's this one say? This one says x1 prime is what? It's y prime, right? What's y prime? x2, right? So x1 prime is equal to x2. How about y prime prime? What's y prime prime equal to? Well, up here, we've got, this says what? This says y prime prime is equal to what? Minus 3y prime minus 2x, which is what? Minus 3x2 minus what? 2x3? So x2 prime is actually equal to minus 3x2 minus 2x3. How about x3 prime? What's x3 prime equal to? That'd be x prime, right? But what was x prime? X prime we said was x4. So x3 prime is equal to x4. And how about x4 prime? What's that going to give us? That gives us x prime prime. But you notice that the equation up here, we can solve for x prime prime. X prime prime equals to, what we got? Minus y prime prime minus x, which we already learned y prime prime was minus 3x2 minus 2x3. And x was defined to be x3, so that's minus x3. So therefore, x prime prime is